Have you ever wondered what makes the lights flicker just a tiny bit, or why some electronic devices hum softly when they are plugged in? Or perhaps, how your sensitive electronics get that perfectly steady flow of power they need to work reliably? It all comes down to maintaining a pure direct current and overcoming an inherent challenge in power conversion. Rectifier output ripple originates from the incomplete filtering of the alternating current input signal after it has been converted to pulsating direct current. Essentially, it is the small, unwanted alternating current voltage component that remains superimposed on the direct current output of a power supply, even after the initial rectification process. Let us break down why this happens. Rectifiers are devices that convert alternating current, which regularly reverses direction, into a pulsating direct current, which flows in only one direction. However, this pulsating direct current is not perfectly smooth. It still contains significant variations in voltage, resembling a series of humps. To smooth out these humps and achieve a more stable direct current, a filter capacitor is typically connected in parallel with the load. The capacitor charges up to the peak voltage of the rectified waveform. Then, as the rectified voltage drops, the capacitor begins to discharge through the load, supplying current and preventing the output voltage from dropping completely to zero. The time it takes for the capacitor to discharge and the load's demand for current directly influence the ripple. A higher load current draws more quickly from the capacitor, leading to a larger voltage drop before the next charge cycle. Similarly, a lower input frequency means the capacitor has more time to discharge between peaks, resulting in greater ripple. Conversely, a larger capacitance value allows the capacitor to store more energy and discharge more slowly, which reduces the ripple amplitude. Engineers mitigate this ripple effect by carefully selecting the appropriate filter capacitor values for a given load and frequency. For more demanding applications, advanced filtering techniques are employed, such as incorporating LC filters, which use both inductors and capacitors, or by integrating voltage regulator circuits. These additional components further smooth the power, ensuring a clean and stable direct current supply that is critical for the reliable operation of sensitive electronic components, protecting them from noise and instability. A key metric in power supply design is the ripple factor, often expressed as a percentage. It is defined as the ratio of the root mean square ripple voltage to the direct current output voltage. A lower ripple factor indicates a superior filtering performance and a higher quality power supply. Understanding and minimizing ripple is not just an academic exercise, it directly impacts device performance. Significant ripple can introduce noise into analog circuits, cause erratic behavior in digital systems, lead to overheating, and ultimately shorten the lifespan of sensitive electronic components within any device. By understanding the fundamental mechanism of rectification and the critical role of filter components, we can appreciate how a well-designed power supply ensures a stable and clean direct current power source. This meticulous approach to smoothing out inherent alternating current variations prevents a multitude of operational issues, safeguards delicate circuitry, and ultimately extends the functional life of our electronic devices. It is a cornerstone of reliable electronics,